Okay, so for this video we're going to solve the problem that's on the screen, and this is an optimization problem from calculus. And basically what it boils down to is we want to find the minimum cost for making the can with the given conditions in the problem. And so we're told that our can is cylindrical, so maybe a picture helps. I don't know, they always say a picture helps, so we'll go with that. We can try to sketch out a cylindrical can. And so our cylinder has some height, we'll call h because it's not given, and some radius we'll call r because it's not given. So what information are we given? The cost of the materials for the top and the bottom of the can, 10 cents per square inch. Cost for the material for the rest of the can, 5 cents per square inch. And the can must hold 500 cubic inches. Well, there's something maybe we can use. We know that the volume of a cylinder is the area of the base, which is a circle, pi r squared, times the height, which is h, and we know that that volume must be 500. So there's something we can maybe work with. Okay, and we need to use this 5 cents per square inch and 10 cents per square inch. So can we set up some equation that represents the cost? Okay, well let's start with the 10 cents per square inch. That's the cost of the material for this top of the can, which is a circle, and also for this bottom of the can, which is the same circle. So we've got two circles, both of area pi r squared, and we have 10 cents per square inch. So we want to multiply all of that area times 0.10 or just 0.1. Okay, now we also need to add to that the cost for the rest of the can, which is 5 cents per square inch. So how am I going to figure out the area, or the number of square inches, for the rest of my cylinder? Well, what I'm going to do is imagine if I could make a cut down one side and then unravel the cylinder. So maybe an easier way to imagine it is if you take a piece of paper and you roll it up into a cylindrical shape. Of course, you can always unroll that piece of paper and set it flat on your table, and if you do that, it looks like a rectangle. So if I had a piece of aluminum, I would need to cut it before I could do that, and then unroll the cylinder. Whoops, never mind this. This was something I was writing earlier. We'll get to that in a couple of minutes. But anyway, I was saying if we come down and we unroll this, just like you could unroll a piece of paper that was rolled up, and we could lay it flat on the table and we'd have a rectangle. Much easier to think about finding the area of a rectangle. Right, so this side, or I guess maybe this side on my cylinder corresponds to this side of my rectangle, which is the height of the cylinder. Right, now this side on the rectangle was the top of the cylinder, which is now unrolled. Right, so the top of the cylinder came down and is now that side of the rectangle. And so we could find this distance on this leg of the rectangle if we just found the distance around the circumference of the top part of the can. So in other words, we just need to know how to find circumference, which is 2 pi r. So the area of the rest of the can, the area of this piece here, is 2 pi r times h, and we know that that's 5 cents per square inch. So we're going to have 2 pi r h times 0.05. Okay, now let me maybe simplify this cost equation a little bit. I've got 2 times 0.1, which is just 0.2. I've got 2 times 0.05, which is just 0.1. And where I'm at is I want to find the cheapest possible can. In other words, excuse me, I want to take this cost function and minimize it, which in terms of calculus, that means we want to take the derivative, set it equal to 0, and solve. The problem is that I've got two variables in this cost equation. I've got an r and I've got an h. That means that I need to have another equation to use, and I do. Another equation that involves r and h. So I'm going to take my volume equation and you could solve it for either r or h. I'm going to solve it for h. And then I'm going to go plug that into my cost equation. And then I'll have my cost equation all in terms of just r, the radius. Let's see, plug that in for h. So we'd have pi r times now 500 over pi r squared. So some things will go away here. This pi and this pi will cancel. This r will cancel out with one of those r's. And so what's left? I've got my cost equation plus, okay, now I've got 0.1 times 500, which is just 50. And I'm left with an r in the denominator, so that's 50 over r. Right, 0.1 times 500 is 50. This guy and this guy are gone. All that was left in the denominator was r. So now I've got my cost equation completely in terms of r. Now I can take the derivative of the cost with respect to r. So just use the power rule. Remember, these are just constants, so leave them there. I'm going to multiply 2 times 0.2 using the power rule. The constant 50 can stay where it's at, and then I'm doing the derivative of just 1 over r, which is negative 1 over r squared. Should be a derivative you've done quite a few times. Set that equal to 0, and now I just need to solve this for r. So I'm going to add this term to the other side of the equation. Then I'm going to multiply both sides by r squared. These go away over here. So this gives me 0.4 pi r cubed equal to 50. And I'm going to divide both sides by 0.4 pi. And then to get r by itself, I simply need to take the cube root. And trust that you have a calculator handy where you can punch that in, and you'll get approximately 3.41. Now that would be for the radius, and I think we were measuring in inches. Okay, and then to get the height, you would just go back to your equation that we're using for the height, and we would plug in the radius there, so we can plug in our value of 3.41 what was that? Divide by pi r squared. And that should come out, I actually don't have that number written down, so let me, whoops, and of course, I don't want to do 500, just 50. Oh, I'm sorry. No, I do want 500, because that was what I got when I solved for h at the beginning, so I take that back. I do want 500, so let me punch this in real quick. I apologize for not having this prepared a little better. Let's see, 3.41 squared times pi, and then I'm going to divide 500 by that. And that should come out to be about 13.69, and again in inches. So there you've got the radius, and there you've got the height. Of course, I had to round those to 2 decimal places, so if you wanted to keep the answers exact, maybe you would just leave your answer like that for the radius, and whatever. You could leave it like this for the height, but personally, I think it's always better to have numbers, so we have a good idea of exactly what that radius and that height should be. But anyway, I think that gets us to our solution.